Welcome. In this session, we'll learn how to define complex real reactive and apparent power of an element. So let's start. Now let's start with the definition of a complex power. So how do we define complex power of an element? Okay. So if we suppose the voltage in with respect to time is defined like this: Im cos omega t plus theta I, where Im is the amplitude of this current, omega is the frequency, and theta is the phase. So from this we can write the current phasor I is equal to Im at an angle of theta I. This is how we define a phasor of a sinusoid. So same way, if we say the voltage across the element is V of t, which is defined as Vm cos of omega t plus theta v. So this is the voltage across the element. Then from this voltage, we can define the voltage phasor as V equal to Vm at an angle of theta v. So these are the voltages and currents through and across this element. Okay. Of which we want to calculate this complex power. This capital I is the current phasor and capital V is the voltage phasor. All right. Now, one thing to note here, that we are assuming that Im and Vm are peak values, are maximum values. Our peak, let's also call it the maximum values of current and voltage respectively. Okay. So we are assuming these are the peak values of this current and voltages. So how do we define the complex power? Now the complex power is denoted by the capital letter S, and it is defined as voltage phasor multiplied by the conjugate of the current phasor divided by 2. So if voltage is given in terms of the peak, there's peak value Vm, and current is given by the peak value Im, then complex power is defined something like this. So if we substitute the value of the V phasor, we can write. So from this, we can write V phasor is simply Vm at an angle of theta V, and complex conjugate of this I phasor will be simply Im at an angle of theta I. Now complex conjugate means simply replacing theta by minus theta, or in terms of a rectangular form of a complex number, we say replacing j by minus j. That's what conjugate means, divided by 2. So this is how the complex power is defined. Now we can a little bit manipulate this expression, so we can write it as Vm at an angle of theta V. Let me simplify it. So it is Vm Im at an angle of, simply the angle is add here, theta V minus theta I. So theta V minus theta I divided by 2. So this is the complex power. All right. Now we can further write it like that as Vm at an angle of divided by under root 2 Im under root 2 at an angle of theta V minus theta I. All right. So what is the maximum value divided by under root 2 for a sinusoid or cosinusoid is referred as the RMS value of the quantity. So voltage, maximum value of the voltage divided by this divided by the root 2 is referred as the RMS value of the voltage. So we can write it as, so complex power S can be written as S is equal to V RMS I RMS at an angle of theta v minus theta I. All right. Now you know this is same as this is simply VRMS IRMS e to the power j theta v minus theta. This form and this form are one and the same thing. Okay. This is referred as the magnitude and phase form, or simply the phasor form. This is referred as the Euler form. All right. Now here we have put VRMS is simply equal to Vm divided by under root 2, and IRMS is referred as simply Im under root 2. All right. Now we know from Euler form we can express it like this. So we say this is simply VRMS IRMS cos of theta v minus theta I plus j VRMS IRMS sine theta v minus theta I, because we know e to the power of j theta is simply cos theta plus j sine theta. So this is referred as Euler's identity. So this is referred as simply Euler's identity. So this is the complex power. All right. Now we can put this complex power like this. So we can write it S is equal to P plus JQ. So this is how we define this complex power. It has a real part and imaginary part, where the real part is simply referred as the real power, or this is also sometimes referred as average power absorbed by the element or delivered by the element. Average or real power delivered by the element, and it's given by simply VRMS IRMS multiplied by cosine of the phase difference between voltage and current. Okay, so this is how we define this real power. Okay, so this is the power absorbed, real power absorbed or supplied by an element, depending upon whether the element is source or this passive element. All right, so this is the average power of the real power of an element. Okay, and it is denoted by simply P. So P is simply equal to VRMS IRMS cos of theta v minus theta I. So if we substitute back the value of VRMS and IRMS here, so if we substitute it back here, so we can also write it in terms of maximum of the peak value. So we can write it as Vm I maximum divided by 2 cosine of theta v minus theta. So this is the expression of this real power or the average power across the element. All right. So this is how we define the real or the average power from this. Now, what is Q? Q is simply called, so Q is simply called the reactive power. So Q is simply called the reactive power or the stored power. So Q is simply called the reactive power, and it's given by VRMS IRMS sine of theta v minus theta. Okay, so this is how I define this reactive power. So it is denoted by the capital letter Q. So Q is simply VRMS IRMS sine of theta v minus theta I. Now, if we substitute again the value of VRMS and IRMS in terms of the maximum or peak value, we can write it as Vm Im divided by 2 sine of the phase difference between voltage and current. So this is how we define this reactive power of the element. So this is the power. Okay. So this is the reactive power. Now a little bit about the units. P is denoted or measured in terms of watts. We say power absorbed or supplied, real power absorbed or supplied by the element is the VRMS, IRMS cosine of theta V minus theta I watts, and the reactive power are the imaginary part of this complex power is denoted in terms of volt, ampere, is reactive. We'll see the meaning of what is meant by reactive here, hopefully in the next class. Okay, and it is denoted in short by VAR. Okay, VAR means volt, ampere, reactive. All right. Now, so these are the units of this P and Q. So if I take the magnitude of this P, I can say, sorry, S, I can write as S is defined by P plus JQ, where P is equal to this quantity and Q is equal to this. So if I take the magnitude, and we know how to take the magnitude of a complex number, so we can write it as S magnitude, which is equal to under root of P square plus Q square. So that means it is the square of these quantities. So if you take the square of this quantity, P and Q, what will you get? You get simply VRMS, IRMS, cos of theta V minus theta I whole square. This is the definition of P, plus Q is VRMS, IRMS, sine of theta V minus theta I whole square. And we can write it as, you can see both the terms have VRMS and IRMS as common, so we can take it out. So we can write as, VRMS, IRMS whole square times cosine of theta V minus theta I whole square plus sine of theta V minus theta I whole square. Now we know, we can write it as, first let me write. So we can break it into the two roots. So we can write it as VRMS, IRMS whole square times under root of cosine of theta V minus theta I whole square plus sine of theta V minus theta I whole square, right? So from here you can see square and root will cancel. So we'll be left with VRMS, IRMS, right? And multiplied by, what is this? We know the identities cos square theta plus sine square theta. Sorry. So this is equal to 1. We know this is equal to 1. So this time it is cosine square theta V minus theta I plus sine square theta V minus. So this is simply under root of 1. Okay. Now under root of 1 is simply 1. So that means the magnitude of this complex power is simply defined as VRMS, IRMS. Okay. So this is simply, so this is the magnitude of this complex power. And the unit is volt amperes. So the unit here is volt ampere, or simply VA. So it is denoted by VA. All right. So this is how we define this complex power. And this is referred as the apparent power. So S is equal to Vrms times Irms is referred as the apparent power. Okay, this is referred as the apparent power. So this S equal to Vrms Irms is simply called the apparent power. Okay. All right. So this is referred as the apparent power. All right. So this is define how we define the different types of power. So S is simply called V times I conjugate divided by 2. If the quantities are defined as peak values. So if these are defined in terms of this RMS values, then this is the definition. Okay, then we get the real part and the imaginary part of this. We say the real part is called the real power or the average power. Okay, real part or the average power supplied by this element. Q is called the reactive power. Reactive power supplied or consumed by the element, depending upon whether it is source or simply a passive element. And if we take the magnitude of this, we get the definition of the apparent power. Now, so the complex power, we have the definition. So we got S is equal to P plus J Q. So we can draw it. We know if how to draw these complex numbers on a complex plane, or how to plot the vector. So if you say P and Q are vectors, so if you say P is in this direction, then Q is at an angle of 90 degree, because we have a J term with it, so we can write it like this. So this is Q, so this is the magnitude of P, this is the magnitude of Q. Then if we add them vectorially, we know from vector algebra, we'll get the S. Okay, we'll get the S. And this is referred as that theta V minus theta angle, or if we simply call it theta. So if I simply refer this as theta, where theta is simply the phase difference between voltage and current. Okay, so this is the magnitude of this. So how do we define cosine of theta here? Cosine of theta, which is same as here, cosine of theta V minus theta I, which is defined as P by S. If we say these are the magnitudes, okay, how do I get it? If we say these are the magnitudes, what is P defined as? It is simply defined as Vrms, Irms, multiplied by cos theta V minus theta I divided by S. How is S defined? It's simply as Vrms, Irms. So Vrms, Irms will cancel, right? So these will cancel. So you can see now, this is simply equal to cosine of theta V minus theta I, indeed. And this is referred as power factor. So this is defined as the power factor. Power factor. In short, PF. So PF is defined as the cosine of the phase difference between voltage and current. So this is referred as the power factor. Very important term for power calculations. Very, very important. Okay, well, I hope you have got the meaning of these different terms here. So this is simply referred as power triangle. This is referred as power triangle of the circuit or element. This is referred as a power triangle of the circuit or element. This is how we define the different quantities. I hope you know how to plot the complex quantities, okay, on a complex plane, right? So if we say this is the real part is plotted on this side, like the x-axis. Imaginary part is plotted on the this y-axis side, or simply the j-axis side. All right. So this is how we define these different quantities. So we have defined the complex power, and the unit of complex power is simply VA. And we have defined the real power, reactive power, and apparent power. Okay, and we're seeing the definition of this power factor. So power factor is simply defined as the cosine of the angle phase difference, or the angle difference of the angles between voltage and current. Okay, so this is how we define these different quantities. All right. Now, in the next session, what we'll do, we'll see what is the meaning of these terms. P, Q, S, and power factor for different elements. Okay, for the elements like resistance, inductor, and capacitor. All right. So let me end this session here. In the next session, we'll continue.